body diagrams, free body or force diagrams. And then, so once the diagram is done and you know what you're doing, you set up. So this is like step 1, and the step 2 would be set up the force equation, let's say. But the force equations in general. So let's take some cases, because this is why it becomes difficult, because you are trying to really get into the heart of learning how to do this. So let's say you have a block. So for now we'll talk about solid blocks. Nothing floppy, it's not like a block of jello. It's just a solid block. Think of it as a wooden block or something. And let us say that this block has a certain mass m. And for practical purposes, although we will define these issues much later, we'll think about the mass as being concentrated entirely at the center, at the geometric center of this object. It's called center of mass, but we'll come to a more proper definition of center of mass later. We don't need it now. So as far as you are concerned, this block has a mass, and we can imagine that the mass is concentrated at the center only, and there is a downward force due to gravity that will be mg. I'm not putting in vector signs yet, but you can. So we know from Newton's third law that there will be a force coming from the surface, because the surface is supporting this block. So we will be able to write that there is an upward force. We can call it F surface for now. We can call it F normal. Somebody was asking me, I think Johannes was asking me, that what if I call it a normal force, because I'm used to calling it a normal force in my AP physics class. That's fine as well. But I prefer to call it a surface force, because specifically it's coming from the surface right now. So let's now say that I am applying a certain force F forward by pushing it forward. And let us say that this surface has some friction, and we will get into defining friction in more detail later, but let's say it has some friction, and this friction is an opposing force here, because friction always opposes. Friction never helps you. The whole idea that you have a friction force coming in necessarily means that it's a force that opposes or hinders some motion, or even a tendency to motion, to move. So let's say friction force goes the other way. So several things can happen. First of all, because this thing is stable as far as the vertical axis is concerned, we would certainly be able to write, if we take this to be the positive direction, Fs, which is the positive quantity here, minus mg. And since the net force along the vertical direction is 0, because this is not accelerating upward or downward, we should be able to write this as 0. In other words, we know that Fs is equal to mg. Okay? So be very careful here, because this is where you will really fall apart if you don't understand completely what it is that we are doing. So in other words, you have Fs, you have mg. I'm talking about what's happening, let's say, on the y-axis. All right? So on the y-axis, you have Fs upward, mg downward, so Fs minus mg is 0. There's no net force along the y-axis. So what's happening on the x-axis? Well, let us say this force wins over the friction force in such a way that there is a net acceleration forward that way. You can turn it off, but let's say it's there. So I will take the right side. So this is the x-axis. What's happening along the x-axis? So I will take the right side to be the positive sign. So that will be F here, which is the force on the right. Friction is the opposing force minus friction. So the net force will be the mass of the object times the acceleration. So on the right side, what you are putting down is what is ultimately happening. So the ultimate thing that's happening along the y-axis is that there is no net force. The ultimate thing that's happening along the x-axis is that you have some kind of a mass times acceleration as far as the block is concerned that you can, let's say, measure. So some kind of a net force remains there. So the net force is what? The net force is F minus F friction. That is the actual vectorial sum of the two forces at play. Any questions so far? All right. So let me now ask you a question and see where you end up. Imagine you have a suitcase, a piece of luggage. Let's not draw the wheels right now. And let's say there is a mass mg downward, and let's say I am applying a force in this direction. I call this force P. Okay? And let's say there is a friction force here. And there is going to be some kind of a surface force here also. And there is some relative acceleration this way. So a lot of things are happening, except the only change I've made is that instead of applying the force horizontally, I'm applying the force at some angle. So let's now define that angle, and let's call it theta. So what will happen vertically, do you think? What are the upward forces? You have seen this before. The upward forces, there's an Fs sitting around already, right? But you see this P will have an upward component. In this case, because that is theta, that will be P sine theta. So plus P sine theta minus mg is equal to 0. So it's interesting, isn't it? Actually, when you pull a suitcase, you are reducing the net upward force that you are dealing with. Or in other words, what appears to be its weight. So this is what appears to be the weight actually. When we talk about weight, that's actually what we are talking about. We're not talking about mg in general. This is what we're talking about. So that's why I said weight is a very tricky thing. So now as far as the x, so this is the y-axis. So as far as the x-axis is concerned, I'll have p cosine of theta. So that's my actual force forward. Minus the friction force, and that would be equal to the net force that's resulting in the acceleration A for the mass x. So these are going to be the equations of motion that we have for this block. Any questions so far? Ask me questions, because this stuff, you'll be dealing with this stuff intensively. Yes? Say that again? We are not really considering the friction. We are assuming it's moving. So that is, yeah.
Will the force of friction always be negative?
You have to be a little careful. Force of friction can always be negative, but in what respect? Force of friction is always an opposition force. So it ultimately depends upon your choice of what is positive and what is negative. Right? But it's always an opposition force. It's not really something that really helps you. Somebody had here.
Because the wheels of the take over force the body.
Sure.
Isn't because the vortex wheels take over the force of the P for the Fs.
I still don't understand your question. Basically what's happening is that if you apply the force this way, then Fs and mg are the same. If you apply the force that way, then your thing might go up even, or Fs will change, right? So when you apply somewhere in the middle, we know by resolving vectors we have a forward piece and an upward piece. So the upward piece, Fs and the upward piece will be coming in. So if you look at that equation, Fs will now be reduced than what it was before. Because previously Fs was mg. But now you see Fs would be mg minus P sine. So the effective weight that you will feel, the effective weight is your Fs. Because that's what your hand feels as it tries to lift it, if it were to be lifted. This would now be less. But that's the reason why when you roll a suitcase nowadays, you roll it at an angle. because the effective weight of it is reduced instead of actually dragging it. Any other questions? Yes.
Force of friction is dependent on the mass of the object.
I will define it for you later. But force of friction basically depends upon the normal force. So in this case, the surface force and the coefficient of friction itself. So friction again is a tricky thing. So you need to understand concepts like whether it's kinetic friction, which is associated with moving objects, or static friction, and so on. So that's a whole different section. That's why I didn't want to break this down. By the way, in next week's lecture, you will see that I talk about the force of friction in great detail and how to do that. Yes?
So if there's a force on either side of the mass, what side would like the force of friction fall on?
Force of friction will always oppose the tendency or the actual motion in the given direction. So in this case, if we take the motion to the rightward, force of friction to the left, and vice versa. So friction, therefore, is always a nuisance. It's always going to hurt you. It never really does. Okay. So let's now spice things up a little bit. So let us say instead of putting it on a flat surface, I put it on an inclined surface, right? So an inclined surface, things will get kind of interesting, and you will make lots of mistakes. So I want you to kind of get on the right track right now. So when we talk about an inclined surface, we talk about the angle of inclination, because that's what defines what kind of inclination you have. And let's say this angle of inclination here is going to be called theta. Whatever theta means, some number. So now let us say that I actually have a block here. Okay? I have a block here. And this block has a certain mass. So which direction will mg act in? Vertically down. Straight down.
It's not connected to the vertical surface.
Huh?
Is it like connected to the equal surface? Where the block is?
That is my question to you. What do you think?
Yes, it does.
When you hang from the edge of a cliff, which I have, by the way, is no fun. Almost died in that one. So when you do that, which way does your weight act? You're hanging for dear life.
They're connected to the
Huh? Does it go along the mountain or downward? You're going to fall down. You're not going to go to the mountain. So that's why I was scared shit that time. So basically what happened is that mg is like this. I didn't know I was going to go rough climbing. That was my fault. But it was the scariest experience I had. It was a 4-hour rough climb in South Korea. Anyway, so mg. But I was much younger. It was 1997. All right. So now, pay attention here. Now what happens is mg, first of all, mg is always vertically down. If you ever put mg along the incline in any of the quizzes, I will personally murder you. Because that is the dumbest thing you can do. Think about my rock climb. Alright, so now you're like this. So you have an axis, okay, so you have an axis along the incline. We'll call it the x-axis. That's traditionally how it's done. Most of the time anyway. That's the x-axis. This is the y-axis. For now. Let me show you a super easy way of not screwing up angles here. So if this is the angle here, notice that this line is perpendicular to this surface here. And that line is perpendicular to that surface. Okay? So think about it. This line is perpendicular to this surface, and that line is perpendicular to that surface. So which angle is going to be taken? So what if I do this? What if I turn by 90? Which angle is taken? Sylvia?
The one where the arrows point down?
Here? Yes. So this is the theta, right? So therefore, I should be able to write mg cos theta going this way, and there should be a surface force coming up. I'll call it F sub s. Okay? And let's say I happen to pull the block that way too. Don't ask me what. And because I'm pulling the block that way, which way would friction be? Opposite direction. So downward along the incline. So this would now be the friction force direction. Okay? So far so good? Any problems? Alright. So let's see if we can now set things up. So as far as the y-axis is concerned, this is what's going to happen. So this one would be mg cosine of theta. I'll have an fs going upward. So I should be able to write fs minus mg cosine of theta is equal to 0, because there is no acceleration as far as I know along the y-axis, up, down, up. Alright, so now you see we are in for trouble because we have to do the more difficult problem of doing the x-axis. So as far as the x-axis is concerned, I know that f is upward. So I can choose this to be my positive direction, there's no harm. So I can write f, and of course, if f is upward, if f is winning, let's say, then there should be an acceleration at play coming along. Alright, so friction will be opposing me. What else is there? Is there any other force that is acting along the incline? F is upward, friction is opposing. You tell me.
Gravity.
Okay? Yeah, so what about that? What do you call that for? I mean, what is the formula for that? If you have mg cosine theta going inward, mg sine of theta would be going along the incline, right? That's a no-brainer. So if this is mg cosine theta, this piece, then this piece is going to be mg sine of theta, naturally. So you see, that will also be opposing my f. So minus mg sine of theta is equal to mass times the acceleration. So these are my equations of motion then on an inclined plane. I'm not saying this is easy to do, but this is how you set it up. If there is no acceleration at the end of the day, but it has just a tendency to move up, then the right side would be 0. Then the net force would be 0 on the right side. Everything come up. So read the book, because the book lays this out more systematically in some sense for you to slowly absorb. I'm giving you the real hardcore, because that's where you need to get up to speed very quickly. So let us do something in which nothing is moving. So let's say you have a nice painting that you want to hang on the wall. This is your painting. Okay, so we know that if you want to hang a painting, there are many ways of doing it. Suppose one way is that you have a nail here or something here, and you have two strings that hold up your painting. And let us say you know what these angles are. And let's say, for argument's sake, they are 60 degrees each. So this is an equilateral triangle. 6, 6, 6. All three must add up to 180. That's okay? So far so good? Any objection? I can hang a painting. No problem. Perfectly legal. So now you see, I have mg downward because m is the mass of the picture, along with the frame and everything else. G is acting downward. But this thing is not falling. This thing is being held up, right? This thing is being held up by those strings. The way it works is as follows. This point is fixed. This is not moving. So the net downward force must be balanced, the downward force must be balanced by the net upward force. So what happens when you put strings like these? Well, what happens is that the strings, in reality, the strings actually stretch a little bit, and become pretty tight because they're holding it up, and settle in. So they are like straight and tight, usually. So in this case, let's first think of that picture that we have, that the strings are tight. And so what will happen is that this if you look at the string will try to hold it up because otherwise it will fall, which means that there will be some kind of an upward force acting along these two strings. So when forces act along strings, and because everything is identical, both of them, in this case, we'll say, has tension T. Tension basically is the force being transmitted by the string. Okay? So strings are so normally when you have a string, it's a tension. So if you're driving down the Golden Gate Bridge, you will find that the whole thing is being held up by all these zillions of wires. These are actually extremely strong wires. They're not that thick. They're not like thick or anything. So all of them, they're very tight, and they carry the tension that they need to carry to support the entire structure, along with, of course, the columns and so on. So in this case, the string that's doing it. Now I have to be a little careful, because the point is, if these strings have a mass, then if you apply, if it's transmitting a force, the string will actually, some amount of the force will end up in actually stretching the string. So we make an assumption here. We kind of make it very mechanically in books and so on, but in reality, it's a practical assumption, because incorporating the force associated with the stretching of a string is not an easy thing. Furthermore, it's a relatively tiny effect compared to the real problem. In fact, most decent strings would stretch a really small amount. You wouldn't hold a picture like this with a rubber band, right? Because that would be highly elastic, and that won't be a good thing to do. In fact, the whole thing will start to bounce. So we normally would use a very good string, and typically what will happen is that the mass of the string is extremely tiny. So for all practical purposes, without really making much of an error, we will assume that the strings are massless. So whenever we see strings from now on, until the end of the semester, unless I tell you otherwise, you will assume that the strings are massless. So is that real? Can something be massless? Something can be massless. Strings are not actually massless. But for typically the masses we are interested in, this is extremely tiny, so we can safely ignore whatever mass it will have. So therefore, these are massless strings, and massless strings have a very nice problem. Because they don't have mass, they don't have to stretch or use up this and that. In other words, they're perfect transmitters of force. So a massless string is a perfect force transmitter. So what we can now say is that we can resolve so whenever you see forces at an angle, what should you do? You should have the incredible urge to split them up correctly along x and y axes, right? So now you see I have the urge to split it up along x and y axes. So if this is 60, I would say t sine 60 would be the vertical component for each of them. So the total vertical force coming from the strings is 2t sine 60 minus mg. That must be equal to 0 because this painting is in equilibrium. It's neither going up nor going down. There's no net acceleration involved. Now, what happens to the other piece? So for instance here, if I take the horizontal piece, I have a t cosine theta, right? T cosine theta going to the right. But for this guy, I have a t cosine of theta going to the left. So t cosine of theta here and t cosine of theta here will cancel out. So in other words, along y-axis, nothing will be happening. Along x-axis, nothing will be happening. There is no net force. Along y-axis also there is no net force. The net upward and the downward forces will balance out. So you will be seeing a lot of problems like this. In fact, I have already given some problems, at least one problem like this in the homework And in the lecture on Tuesday, I take you through some of them. So I'm going to skip that because since I'll be doing it down the road, I don't want to repeat it and waste time. Any questions so far? Any questions with what we have done so far? If you have questions, you can clarify. Yes.
Would this tension only work like in upwards direction, or can it like?
Tension is always holding things up, right? So whatever weight the tension is carrying, it will be the direction opposite to the direction.
Will the angles of the triangle, like the t sine of 60 and such, always be equal, or will you have different angles for triangle?
Well, if you ask me, I mean, I typically, on average, would put something like this. I'm very good at doing things slightly crooked. So, that's what would happen. Right. They won't miss it. There is friction, you'll get stuck anyway. So I made life simple by making it symmetric, but it doesn't have to be. So for example, I can have a situation like this, where let's say, I think this is the problem I gave in the homework, where this building is on fire, somebody's hanging here, there's a rope, there's a fireman, blah, blah, blah. But the real problem is that this angle is given, so which means this angle is given, and this angle is given. So you have a tension here and a tension here and an mg here, and you can resolve this tension into a vertical piece and a horizontal piece. Resolve that tension into a vertical piece and a horizontal piece. Add the two vertical pieces, balance it with this. The horizontal pieces must cancel out because this thing is not accelerating to the left or right. The only thing in that problem you have to be careful about, I forget the number, it's somewhere towards the end, is that the angle given for the string on the left side is actually this angle, which ends up being that angle. So if that's the angle, so if you call it T1, then if this is the angle given, then this is going to be your T1 cosine of theta. And that is going to be your T1 sine of theta. And here, on the other hand, if this is, let's say, T2, then this will be T2 cosine of, let's call it, whatever. Let's call it phi, another name. And then the vertical piece would be T2 sine of phi. So in other words, in this problem, I would have T1, so as far as the y side is concerned, I have T1 T1 cosine of theta, because that's the vertical piece for T1, plus T2 sine of phi is equal to mg. And then for the x piece, I'll have T1 sine of theta minus T2, or you can list minus T2 cosine of phi equal to c. So I think these are the equations you get that I don't remember the details of the problem. I think that's what it is. Any questions? So be careful about how the angle will be found, okay? I've been mollycoddling you by giving you angles which you are used to seeing, but I'm not changing the game. Just giving you random angles and asking you to figure out which is the cosine and which is the sine. So whenever you see an angle, immediately figure out which one would cosine be, and remember that there is a 90% chance you might screw it up. So don't be confident, do it soon. Question? All right. Okay, so now we come to the tricky issue of weight. One more time. Okay, so let me put you on a bathroom scale. So that's your bathroom scale. Here you are, and you are standing on the bathroom scale, obviously. So this is your mg. Bathroom scale gives you a reaction force. which is your surface force here, Fs, and you basically, your bathroom scale gives you a reading, and this reading is essentially Fs. You would say, how do you know? It's giving me mg because Fs is equal to m. All right, fine. I accept it. You want that argument. But let me now put you with the bathroom scale in an elevator. So here is the elevator. Here is your bathroom scale. Here you are. Okay? And let us say the elevator is going up. And let us say as it's going up, it's accelerating at some a. So imagine what it is. Your bathroom scale, you in an elevator accelerating up. Very simple. Happens all the time. So now you see, you have mg, and you have your bathroom scale will do you a favor and return you Fs. So now the situation is interesting because I have Fs upward. So I will put Fs first as positive because eventually the thing is going up. So observe what I do here. mg is downward, but the next thing that's happening at the end of the day, okay? Don't screw this up. What's happening at the end of the day? The final result is that you have a mass m, and you also being in the elevator experience an acceleration a upward. Agree or disagree? So this is what will happen to you, right? You will basically find ma as what's happening at the end of the day because you are in the elevator. Elevator is accelerating upward. So now what happens? This is what the bathroom scale gives you. This is supposedly your weight, as I have been trying to convince you. Now you see what happens is that you get m times g plus a because it's mg plus a. So if you are in an elevator and the elevator is starting to accelerate upward, the weight that you will feel would be more than your weight, more by ma, your mass times the acceleration involved. So never measure your weight when an elevator is accelerating upward. You'll get a larger weight. On the contrary, you can find out the acceleration of the elevator. Yes?
Well, if an elevator usually doesn't like constantly accelerates once it like reaches.
Then it's fine. But when an elevator takes off, right, trying to go second floor, let's say, it accelerates. And you know very well how you feel. You feel a little heavier, right? There are some elevators that move pretty fast, and you actually feel it quite a bit. But for slow-moving elevators, it can be a bit subtle. So by the same argument, if I now say I don't want my weight to be increasing, even though I had a big lunch, I actually want my weight to be decreasing. This is my elevator, and now it is beginning to accelerate downward. So I have an mg here, I have an fs that way. Okay, so now if I want to write down the equations of motion, nothing is going on along the x-axis, so we don't really care. So fs is now upward, but the next thing is happening downward. So I'm better off doing it this way. I say, because mg is the downward thing, and mg is being opposed by the fs. So I'm going to read that picture. This is what I was trying to ask you to be careful about, is equal to ma. So observe how I did the signs. I put the winning force, what happens at the end of the day, that direction to be positive. So in this case, I took mg, my downward direction to be positive, and fs to be negative because this is opposing it. Because ultimately at the end of the day, I'm going downward. And on the right side, instead of dealing with the minus sign, I put ma positive. So this is a major departure from the blind rules that I instituted when we were taking baby steps. So now you are presumably grown up, and you don't need to take just baby steps, and it can make your life easier. Now you see what happens is that if I move fs to the other side, I have m times g minus a. So in other words, I will indeed feel lighter. Lighter by how much? Lighter by ma. I can assure you 90% of the class will screw this up if I give it as a quiz on Tuesday. Of course, I won't state it quite the same way. So think about it. Read about it. Try it out in an interview. Convince yourself. Believe it. These are necessary steps. Because physics is all about being able to feel and make a movie in your head about what's happening and figuring it out for yourself. Okay? I can tell you the words, but you won't absorb it unless you experience that. So seriously, you take an elevator, just try it out, see how you feel. Now suppose I do something really mean, which I do all the time. Suppose this is the string, the rope that's holding up the elevator. Suppose I climb up there and as you are going down, I cut it. How would you feel? Weightless? You feel weightless? So that, remember I said I jumped off here and I felt weightless? What?
Like, if we cut there, like, our weight should be like 0,
Yeah, because if I cut it, then the acceleration will become g. So that would imply that your Fs would become 0. That means your weight will be totally weighted. So if you don't even try it here, well actually since Rash is making a video, it would be a nice video piece that you can post on YouTube. You won't fall, I'm sure. I have fallen a few times and hurt myself, so I get scared now. I don't want to limp around. Especially that I have to take a flight after tomorrow to Los Angeles. That won't be fun. So, okay, all right. So you understand then why you are weightless, okay? So let me now ask you, suppose this is a ceiling, and let us say that there is some kind of a spring, there is some kind of a weighing scale here with a little string below it. And let us say you want to weigh yourself in some sort of unusual way like this. Nothing wrong with it, right? So if you do that, what do you think will be measured by this thing? Would it measure your true weight, Fs equal to mg? It should, right? Try it. It should measure your true weight. Actually, it will. So this is the same thing as a weighing scale, except instead of putting your foot there, you are putting your hand and holding it. You look funny, that's it. Okay. All right. Let's now do a somewhat different problem, but it's an important class of problems. And these are pulleys. Pulleys. Pulleys are very important, as you know. You won't have bridges, cranes, nothing without pulleys, right? You won't even have your big buildings anymore. So what's a pulley? The pulley is a wheel like this, which is, let's say, attached to some wall or something. And typically, a pulley at the simplest level has two masses attached to the two ends. Okay? So let us say this mass is M1, and let us say this mass is M2. And let us say I call this string's tension, so M1G would be downward, right? And M2G will also be downward. So I have a tension here, I'll call it T left, and that will be upward because that will be opposing this by Newton's third law. And here there will be a T right that will also be opposing M2G. Right? But if I now tell you that the string is massless, what do you infer from that? Okay, it has no friction. Then what do you infer from that? There's no mass, it's going over the pulley, there's no friction. So, what? what happens by making that huge statement. No mass, no.
Will the two pieces just counteract each other?
No, the masses are not the same. I mean, these masses are not the same. What will happen is that T left will be equal to T right. The tension would be the same. If there is no mass and there is no frictional loss as it goes over the wheel, then the tension would be the same. In other words, once again, we are making the same assumption that we did for the painting that I hung, where the string was massless and a perfect transmitter of force. The same thing applies here. This is, you can imagine that the string is effectively massless and a perfect transmitter of force as a result. All right. So let us set up the equations for this guy and that guy. This is something you really got to learn because this is very, very important and this is very true. So first I got to assume in which direction this thing will move. So let us say this thing moves downward here, and let's say it moves downward here at some acceleration A. So if this is moving downward here at some acceleration A, you agree with me that this is going to move upward with some acceleration A, right? Any objections to that? All right. So if that is the case, then I should be able to say that this is the winning force. M2G is the winning force on for the right guy. So I'm just focusing on this story here. So I'm going to set up, this is the free body diagram or the force diagram for M2. And I'm going to set up the life story of M2 in terms of my equations. M2G is downward, minus T. T left and T right are the same. So I call it T is equal to M2A. So that's my equation for mass M2. All right? So now let's do the same thing for mass M1. So as far as this guy is concerned, this guy is going up. So if this is going up, then the tension is the one that's pulling it up. So I would write it as T minus M1G is equal to M1. Now this is very different from what you have seen so far. So I am actually doing two different things in terms of signs and so on for the two different cases. I'm not using upward as positive and downward as negative as my guiding principle anymore, because that is no longer convenient. In fact, that is downright inconvenient. So what I'm doing is, I'm saying, I'm just going to focus on this mass. This mass is accelerating downward, so I have M2G pulling it down, being opposed by the tension. And the net outcome, M2G minus the tension, is M2A. That's the story of this guy. One correct, consistent story. As far as the left guy is concerned, I'm saying that this guy is being pulled up now because of the pulley. So if this is coming down, that's going up. So I would write this tension, which is beginning the day, minus the opposing nuisance, which is M1G, is equal to M1A because it's going up. Yeah?
Is tension, what are the units?
Force. Tension is the force. Because tension is essentially the force being transmitted to the massless string. The tension is the force. All right? You guys are okay with it? Yes. It will cancel out mg if acceleration is 0. Because the string is a perfect transmitter of tension. Tension comes because of the two weights on the two sides, right? So the argument, but the tension is not individually equal to this mg and that mg because there is a resultant acceleration. Only if the two masses are the same, then the tension and the two weights would be the same. But that doesn't mean it's not going to move. That only means it can't have acceleration. But even with zero acceleration, you can have velocity. So it can still move. You've got to be careful. All right? Any other question? So typically in these problems, the unknowns would be, what is the tension? and what is the acceleration. So because you have two equations and two unknowns, you can actually solve it. So I will not solve it right now, I'll just give you the answer. The acceleration comes out to m2 minus m1 by m2 plus m1. If you want, you can request Rand's or you can rewrite it next week to work out the details for you. But I'm not here. So you see when m2 and m1 are the same, the acceleration becomes 0, as I promised you. M2 and m1 are the same, the acceleration goes away. The tension, on the other hand, if you now stick this acceleration formula in, the tension that you will get is T equal to 2m1 m2 over m1 plus m2 times g. So it involves both the mass. So what happens if m1 and m2 are the same? This will become m squared, let's say, and this would become 2m. So 2m squared over 2m is going to be m. So that you'll get T equal to mg. If the two masses are the same, just as I told you, your tension will then simply calculate T being equal to mg. Whenever you do these calculations, it is very important at this stage that you work out what the limits are, because that's one way in which you know if you make a mistake. So when I do a calculation like this, I found the acceleration, I know the two masses are the same, the acceleration should be 0. So my formula should give it to me right away, right? And indeed it does, because if m2 and m1 are the same, the acceleration will become 0 because the numerator m2 minus m1 becomes 0. So it must be right, it can't be wrong. That makes sense. So these are the sanity checks that you need to be on top of. Now, one of the things that I would have liked to do today, but I haven't, is Kepler's laws in gravity. That requires a little bit of storytelling because there's a lot of interesting history to that, starting off with Tycho Brahe. But that will wait. In fact, if there is a little bit of time next week, then you guys can discuss the Tycho Brahe problem and how you get the t-squared proportional to r-cube law for planetary motion. And then once I come back, we'll get into work energy theorem and doing these very same problems and more using a very different approach, using energy equations rather than the force equations. All right, get your stuff away. Let's go to the quiz.